Welcome back everyone. This video is going to look at dot point 6.2, which is probably the most important skill when it comes to electrolysis, and that is to be able to predict the actual products that you can get from an electrolysis process. Now, just to remind everyone, an electrolytic cell, which uses electrolysis, the main function of these cells is to produce chemicals, because the energy transformation in an electrolytic cell is you're going from electrical energy to chemical energy. So you will really need to be sure that you know what kind of chemical is being produced from these cells. And you want to make sure that you are producing what you want to produce. So this is the reason why this skill is the most important skill that you need to master when it comes to electrolysis. Okay, so I think I'm going to need to make more than one videos on this topic, but let's just give you some ideas in terms of what influences the products that you can have from electrolysis. So obviously the electrolytes and the electrodes, but I just want to be a little bit more specific here. The first thing that would affect the types of products that you can get is the type of electrode used. So there are two types essentially. You can have an inert electrode. An inert electrode would be something like carbon or platinum. If the electrodes are inert, they will not interfere with the electrolysis process and you would not have to consider them. However, there will be cases when your electrodes are reactive, and that's when the electrodes are made of a metal that could potentially interfere or compete with other substances in the cell to be oxidized or reduced, mainly oxidized. So you can have, say, a copper electrode or a nickel electrode. So that's when you have to be mindful of the electrodes as well. The second thing that could potentially interfere with the types of products that you can get is the concentration of the solution. So 1.0 molar, this is SLC condition, and this is the condition at which your electrochemical series is created. However, you could also have a solution that is very concentrated, like 4.0. You could also have a solution that is very, very diluted, and changing the concentration could affect the products of electrolysis as well. The last thing that it's extremely important to consider is whether or not your electrolyte is molten or an aqueous solution. The difference between the two has to do with the presence of water. If you have a molten substance, say if I have molten sodium chloride, so if the state is liquid, this means that I will have sodium ions and chloride ions. So this is when you take some table salt and then you melt it with no water present. So you do need a very, very high temperature if you're going to do that. Whereas if I have an aqueous solution, this is when you dissolve table salt in water and the state will be different. So you have sodium ion, you have chloride ion still, but if you have an aqueous solution, then it means that you also have water present, and water is going to be a very, very interesting substance for electrolysis. I don't think we really consider it as much in galvanic cells, but it's going to create some trouble, and you will see. So if you just mix and match, let's say if I have an inert electrode with SLC condition and molten, there are a lot of things cases that you can have out of these three different factors that affect the products of electrolysis. So what we're just going to look at in this video is we're going to look at aqueous electrolytes, so when water is present. We're going to look at 1.0 molar concentration, so we're going to keep the concentration as SLC, and we're going to look at inert electrode. So the stuff that I underline here is going to be the focus of this video, and then we're going to look at other things like reactive electrodes, molten electrolytes in future videos. All right, so let's look at the actual steps that you can use for determining the products of electrolysis. Once you get very good, you can skip a lot of these steps. You can do a lot of them in your head, but for now, these are the steps. So you could pause the video and write them down, but I will keep coming back to them. So step one is to list all species present. This is actually very similar to the steps required to determine whether or not a spontaneous reaction will occur, except for, I think, probably the last two steps. You always want to start by listing everything that you have in your electrolytic cell. The second step is to highlight on the electrochemical series. Now, I'm going to discuss this in more details later when the time comes, but essentially all the oxidizing agents that have contact with the cathode and all reducing agents that have contact with the anode should be highlighted. And then we're going to identify the strongest oxidizing and reducing agent present, and you're going to get the half equations from there. So once you get to step 3, step 4 is really easy. And this is probably the one good thing about electrolysis is the half equations actually fairly easy. And most of the time you get them from the electrochemical series. It's just a matter of getting to the right equations. Okay, so those are the steps, and I'm gonna go through how the steps work in a bit. You're going to need your electrochemical series. I took this photo of my electrochemical series. I showed my class this setup last term. You don't have to do it, but it's just a way to make the electrochemical series not as messy if you're going to use it for multiple questions. So you can put it in a plastic pocket. I like to use an orange highlighter. I think that's like somewhere between orange and pink. So you can highlight over it, and then you can quickly wipe it off, and then you can do it for the next question. So it's not too messy. Obviously, it's optional. So as just to repeat what I just said before, the first type of questions that we're going to look at for this video is electrolysis of aqueous solution. So when H2O is present under SLC condition, and we're going to look at inert electrodes. So aqueous solution, SLC condition, which just means in this particular case 1.0 molar concentration for all the electrolyte, and inert electrodes. Okay, that's a lot of talking for not a lot of information. So let's start with question 1. So this is a question, very straightforward. Determine the products formed at each inert electrode. So the question tells you during the electrolysis of 1.0 molar, so concentration is SLC, magnesium iodide solution, so you know it's aqueous. And then you need to draw a fully annotated diagram of the electrolytic cell in operation. Okay, so let's go through the steps. Step 1 is to list all species present. So if you go back to the question, the electrodes are inert, so you don't have to take them into account when you list the species present, which means that everything that I need to work with is the 1.0 molar magnesium iodide. So 1.0 molar Mgi2AQ. This is the first hurdle that you need to be able to go through, and it really depends on how good your year 11 understanding was. Sorry, I probably shouldn't judge your year 11 understandings. But Mgi2 is an ionic compound, and I think this is where things start to go wrong. So you need to be able to recognize that this is an ionic compound. It has a metal, which is magnesium, and a nonmetal, which is iodide. And it consists of two types of ions, magnesium ions, which is Mg2 plus. It is in group 2 of the periodic table. If you follow the octet rule, it's going to lose 2 electrons, all of that stuff. And then you have iodide ion. This is oh my god, people do this every year. This is iodide ion. Okay, so if you look at something like this, the ions are actually present is Mg2 plus and I minus. You have no idea how many times I have seen students splitting this into Mg and I2. That is incorrect. That will be two pure substances that cannot combine together. And also because it's an aqueous solution, the third substance is H2O. Even though I think, oh yeah, okay, so 3 species, Mg2 plus, I minus, and H2O. So I've listed all the species present. The second step is to highlight on the electrochemical series all oxidizing agents that have contact with the cathode and all reducing agents that have contact with the anode. If you think about what is going on in this cell, these 3 substances are in the electrolyte, so they will have access to both the cathode and the anode. I will tell you when they don't have access to both the cathode and the anode. But if you just have a generic electrolytic cell with the 2 electrodes being submerged into the same solution, then every species in that solution is going to be able to come into contact with the electrode. So that's just my roundabout way of saying that I am going to highlight everything out of the 3 here. Okay, so magnesium 2 plus, please do not highlight Mg solid, just highlight the species present. So Mg2 plus is here. There is a water here, and then there's iodide ions, and then there's a water here. Okay, so I've highlighted everything. Step 3 is to identify the strongest oxidizing agent present at the cathode and the strongest oxide-reducing agent present at the anode. So there are only 2 oxidizing agents. The higher one will be the stronger, so that's a stronger oxidizing agent, which is this one. And the stronger reducing agent is the lower one, so that's iodide. Okay. So one way to remember, if you don't know which one is the stronger oxidizing agent or the stronger reducing agent, one way to remember is you always want to form the smallest Z possible between all the species that you have highlighted, because the smallest Z possible is going to be the Z that requires the least amount of energy to happen, because a smaller Z just means that you have a smaller gap between the two species, so a smaller voltage is required. So when you need to predict the reaction for electrolysis, look for the smallest Z possible. Again, this is the opposite of galvanic. When you want the largest backward Z, now you want the smallest Z. And then the last thing that you have to do is just to write the half equations. So this one is going to be reduction. Make sure that you don't include the double arrow. So reduction is 2H2O, and it's very simple. You just need to copy the entire equation. It's going forward, so please don't do the double arrows. So hydrogen gas is actually produced here at the cathode, and notice how water actually undergoes reduction in this case. This is why you have to consider water if water is present, because half of the time it actually is the substance that reacts. And then oxidation is going to be iodide going to solid iodine and 2 electrons. So that's your half equations. You can add the 2 half equations together to get an overall equation. However, that's normally not required in an electrolytic cell, because the 2 half equations don't really have a lot of relationship with each other. Anyway, there you go. And then you need to draw a fully annotated diagram of this cell in operation. So I think I made this checklist a few years ago, which you can use just to make sure that you have annotated everything you have to in an electrolytic cell. But you could also think about what we talked about in the previous video, starting with the 3 essential features of an electrolytic cell. So you need a power supply. That's number 1. Probably can draw a better power supply than me, but I'm gonna stick with this. It's okay. Okay, so you have a power supply, and then you're going to connect the power supply to the electrodes. The power supply is the most significant feature that allows you to distinguish between an electrolytic cell and a galvanic cell. The other one is the fact that an electrolytic cell usually has 1 beakers. However, actual commercial examples, which we will look at next week, are a lot more complicated than this. I think the second one's actually worse than the first one. I'm going to stick with it. Okay, and then we have this. So 3 essential features: the power supply, the electrodes, and the electrolyte. Now, let's do some labeling. We know the electrodes are inert, so I'm just going to assume that they're carbon. You can use platinum if you want. I am going to annotate the terminals of the power supply. So this is a negative terminal, which means the electron is, wow, that's terrible. Okay, electron is going here. So this must be the cathode, because it is gaining electron, and it is negatively charged because we will panic. Positive anode, negative cathode. Electrons will come out of the other electrodes towards the positive terminal of the power supply. So this is the anode, and it is positively charged. Okay, the electrolyte, as mentioned in the question, is 1.0 molar magnesium iodide solution. Okay, so what we have done electrolyte, formula, concentration, state, yes. Power supply, negative and positive terminals label, yes. Cathode, formula, state, polarity, yes. Anode, formula, state, polarity, yes. Flow of electrons, flow of ions. I don't think it's actually applicable here. Let's just go back. So you don't, I don't think you have to do the flow of ions in this case, but if you really want to, so I'm just going to annotate the products. So at the cathode, hydrogen gas is going to come out as the reaction happens. You're going to actually have some iodine solid sinking to the bottom, or liquid sinking to the bottom of the cell. I don't think it can dissolve in water. It forms really weak dispersion forces. And there, potentially there's some movement of ion. The negatively charged ion is going to go towards the anode. So we're just going to say that the OH minus ion is going to go towards the anode. So our anion to anode. We talked about this when we discussed fuel cells, and actually the direction of flow of ions doesn't change in this case. It's still cations to cathode and anion to anode. So this is going to be the flow of ion in this case. And that's everything. You know, if you look at the big picture, it's not a very bad drawing, but let's just this bit is killing me. All right, moving on. Oh, that's another drawing. That's not any better. All right, question 2. Wow, that is a lot of information. So very similar to question 1, at least for part A and B. So you have to determine the products form inert electrode. Okay, let's just take it one step at a time. So let's start with part A, B, and C. Determine the products form at each electrode during the electrolysis of an aqueous mixture, 1.0 molar copper 2 sulfate and 1.02 molar zinc bromide. So what this means is that the two solutions are mixed together into one single electrolyte. And we're going to assume that sulfate is a spectator ion, so you don't, because you're not going to be able to find it on the electrochemical series. You then have to draw a diagram of this cell and then suggest a suitable voltage. I think if you are very confident and you understand everything that I just talked about with question 1, you should pause the video now and attempt at least part A, if not part A, B, and C yourself. So there's your time to do it. I really should come up with a meme for this. Stay tuned. Okay, we paused. All right, let's assume that we have paused and now we're back. So I'm going to go through the question. Okay. So first of all, they tell me, the question tells me, by they, I mean me of last year when I wrote it, inert electrodes. So you don't have to worry about the electrodes. You know that it's aqueous, so water is present, and you know that it's an SLC concentration of 1.0 molar. So the two substances that you need to worry about are copper sulfate, CuSO4, aqueous, and what was the other one? Zinc bromide. Zinc bromide, aqueous. So copper sulfate is once again an ionic compound. It contains copper 2 plus ion and sulfate ions, and obviously water because it's an aqueous solution. Zinc bromide, that should be a 2 here, contains zinc 2 plus ion and Br minus, and also water. So there are 5 species present, and because they are all present in the electrolyte, everything is going to have access to the electrode. So you don't have to worry about this point, at this point in time, I guess. And I'm just going to highlight everything. Okay, so we have zinc ions, which is here. There's a water here. There is a bromide ion up here, and there is a water here. And I've just mentioned earlier that sulfate ion is a spectator ion, so you're not going to have to worry about it. If the question says that it's a spectator ion, it's already implied that it's not going to react. And also you cannot find sulfate on this electrochemical series. Okay, so those are the species that are present, and then I need to identify the strongest oxidizing and reducing agent present, or you can just aim to create the smallest or the shortest Z from everything. So this is the shortest distance that I can have between the two. So there will be a reaction for zinc ions and bromide ions. Oh, sorry, that was very bad. I should have pointed this out, that there's also copper present. Never mind. Should I record this whole video again? I'm not going to do that. Sorry, there is Cu2+. You should highlight everything. Or just understand how your animation works. All right, okay. Now we have the smallest. Z between copper ions and bromine ions. Wow, that was good. All right, I made this video too many times. I'm not recording it again. So the half equation at the cathode, the reduction, it's going to be copper 2 plus, do not forget states, plus 2 electrons going to copper. So that's cathode. And oxidation, you're going to have bromine ions going to bromine 2 and 2 electrons. Okay. What am I doing? Yes, that's reduction and oxidation. What's the next step? Draw a fully annotated diagram of the electrolytic cell in operation. So we have a power supply. And let's just do the electrodes. Oh my god. I need a better writing pad. I'm not gonna buy another one though. I mean, this one works fine most of the time. You just can't do... I think I'm just bad at it. I'm not gonna blame the equipment. I think my sitting position may be wrong. Maybe that's why. Okay, so electrodes, electrolyte, power supply. Let's do some annotation. So negative, positive. This is your, well, it's carbon because it's inert. It just assumes carbon. This is your cathode, which is negative, and that's carbon as well. Question said that this one's also inert, so that's your anode, which is positive. The electrolyte in this case is a mixture of two solutions. I'm just going to list both of them: 1.0 molar copper sulfate and 1.0 molar, what was it? Zinc bromide. I have short-term memory loss. Okay. We need to annotate flow of electrons. So electrons go here and then up. And let's think about, all right, so electrolyte, formula, concentration, state, power supply, cathode, anode, flow of electrons. Let's think about the ions flow. I don't think the ion flow is actually applicable in this case because there's no ion being formed. So there's some copper solid on the at the cathode and then some liquid bromine at the anode. So you don't have to do the ion flow in this case, so not applicable. Okay, so that is going to be the diagram, something like that. Oh, I do want to point out that you can either write the substances in this form or you can write it as ion. So you can go Cu2 plus Aq SO4 2 minus, which some people find more useful because it show you what actually is present, because you don't have a lattice of copper sulfate. You have some ions dissociated from each other. So that's Br2. It's just you do have to write the concentration all the time, and then there's H2O. So that's up to you, whether you want to dissociate the ions or you want to combine them. I think as long as you write the state to be AQ, it implies that the ions are dissolved. The ionic compound is dissolved anyway. Okay, let's talk about voltage. So the question of voltage, and I have kind of already wrote the answer here, is you have to look at the actual reaction that happens. So the reaction that happened here is between copper ions and bromide ions. So this voltage, which is between 1.09 and positive 0.34, so the gap here is 0.75. So essentially what you're after is any voltage higher than 0.75 would do. So I can say 1.0. You can say 10. It's a little bit, don't say 10. Just be reasonable. A voltage of 10 would cause a few issues as well with side reactions, which we'll talk about in the future. So anything higher than 0.75 would be acceptable. Okay, this is when things get a little bit more interesting. So part D of this question asked you to suggest any change to reaction products that may occur after a prolonged period of operation of the cell, assuming a voltage of 4 volt is used. This is a specific type of question, and you know that you get this type of question when they have something along the line of prolonged period of operation. Sometimes they say, what if the cell is running for a very long period of time, what do you think will happen? But sometimes they just say prolonged period of operation. And what they're really trying to say without saying it out loud is essentially asking you to predict what would happen if the cell runs out of copper ions and bromide ions. So if it's a prolonged period of operation, what it is trying to tell you is that, okay, let me just write here, prolonged period of operation, it means that you're going to assume that copper ion runs out and bromide ion runs out. Because if you leave the cell for long enough, all of the copper ions would eventually be converted to solid copper, and all of the bromide ions would eventually be converted to liquid bromine. So there will be a point where you will no longer have any copper ions or bromide ions to react. So if you assume, and you really do want to state these assumptions when you answer this question, is after a prolonged period of time, assuming that the concentration of copper ions is very low or that all the copper ions has run out, then in this case, what happens at the cathode is the next strongest oxidizing agent will react. So if there is no more copper ions, then zinc ion would now be reduced. So at the cathode, you're going to have reduction of zinc ion to produce zinc. And if you leave it for long enough, there is a possibility that eventually also the zinc ions will run out and then you would get reduction of water. At the anode, similarly, if all the bromide ions run out, the next strongest, well, there's only one other reducing agent anyway, which is water, is going to react instead. So you're going to have oxidation of water to produce oxygen gas. Okay, so whenever the questions say prolonged period of time, I think it's safe to assume that it's asking you to consider what would happen if the original oxidizing and reducing agent that were reacting now have reacted completely and run out and you move on to the next one. We're going to talk about how you could calculate exactly when it runs out, but I'll save that for I think 2 weeks from now. So that's just the actual write-up of the answer. You really do want to state your assumption though, that if reaction is happening for too long, assuming that the original ions run out before you move on to your other predictions. And I just want to point out the reason why, if you go back to the original question, actually stated a voltage of 4. Part C just stated we only need something greater than 0.75 for bromide ions and copper ions to undergo oxidation and reduction. However, the reason why the voltage is 4 here is because you would need a higher voltage if you want zinc ions to react. Even so, in order for zinc ions to react, first of all, you need to not have any copper ions to compete with it. But also, in order for this reaction to happen, you actually need a voltage of at least 2 or 1.99. So if the voltage is below 2 or below 1.99, even if there is no copper ions, you're not going to have a secondary reduction and oxidation, just because it doesn't supply enough electrons for the reaction to occur. But most of the time, if the question doesn't tell you what the actual voltage is, you can assume that the voltage is high enough for any reaction to occur. Sometimes I do see a case when the voltage becomes an issue, but not in this case. Okay, question 3, I'm going to ask you to do question 3 yourself. I'm going to upload the solution onto the PowerPoint so you can check your answer there, but you really want to have a look at question 3 yourself and try it. It's very, very similar to question 1 and 2. The only difference is there's a bromo-thymo blue indicator because there's some pH change going on. You did titration last year. The table of indicators actually in the data book somewhere. One of the pages So you can try that and then check the answers using the PowerPoint. That is it for this video.